I am Aijaz. In this lecture, we will study the Cayley's theorem of groups. So, this is the statement of the Cayley's theorem of groups. The states that every group G is isomorphic to a subgroup of Sg, where Sg is the symmetric group defined on the set G. In particular, if order of G is equal to n, then G is isomorphic to a subgroup of Sn. Now we prove this theorem, and we start the proof like this. For A belongs to G, so A is an element of G. Define a mapping. Define a mapping tau A from G into G by tau A of x is equal to Ax. Then it can be easily seen that this mapping is a very different mapping, and we will show that this mapping is a 1-1 onto mapping. Now this mapping is 1-1 onto to show tau A is injective. For showing this, for this, let tau A of x is equal to tau A of y. Then by definition, then Ax is equal to Ay. And this implies x is equal to y. And this follows from the cancellation law in the group G. So therefore the mapping tau A is an injective mapping. Now since this tau A has been defined on a finite group G to a group G, and we know that if there is an injective mapping on a finite set G, then that mapping is injective if and only if it is surjective mapping. So once we have seen that this mapping tau A is an injection on G, so it means that tau A is a surjection. So since G is a finite set or a finite group, in fact this result is for all the finite sets, so we write if G is a finite set, thus tau A is a surjection. So therefore we have proved that tau A is 1-1 as well as on 2. So this means that tau A is a permutation on G. So therefore for every element of G, the mapping tau A defines a permutation on G. So therefore when G has n elements, therefore there are n permutations that can be defined for different elements of G. Now let Sg denote the set of all permutations of G. All permutations of G. Now since this G has n elements, therefore actually this can be written as Sn. So we write Sg is the set of all permutations of G, and let G dash be the set of permutations tau A defined on the elements of G. Defined on the elements of G. Now since each tau A is a permutation on G and Sg is the set of all permutations of G, and we have denoted this G dash to be the set of those permutations from S of G that are defined in this manner for the different elements of G, tau A. So this means that this G dash is a subset of G. Then clearly, the set G dash, this is a subset of G. So this was one nice observation obtained here. Now not only the subset, but we will also prove that this G dash is actually a subgroup of G. Then once we have proved that this G dash is a subgroup of G, then the only thing that remains to be proved is that G is isomorphic to G dash. Now we show G dash is a subgroup of G. Sorry, this is a subgroup of SG. Now before doing that, so for actually doing that, we have to show that this G dash is closed under the mapping composition. Since this SG is a group under the mapping composition, so we will show that G dash is closed under mapping composition. It is associative, it has an identity, and every element has an inverse. Now for doing that, we have tau A, tau B of x. Now this is actually the mapping composition of these two mappings, tau A and tau B of x, for the elements A and B in G. Now by the composition of mappings, this is actually equal to tau A, tau B of x. Now tau B of x is equal to Bx, so this is tau A of Bx. Now by definition of tau A, this is equal to A Bx. Now since the elements A, B, and X are the elements of G, and G is a group, so this is associative, so we can write ABX here, and this is equal to actually tau AB of X. So therefore we have tau A, tau B is equal to tau AB. So it means that the set G dash is closed. Now similarly, we can show that tau A is associative. Similarly, tau A is associative. Sorry, not actually tau A, but the set G dash is associative. Similarly, G dash is associative. Now let A belongs to G. If A belongs to G and G is a group, then A inverse belongs to G. Thus, if tau A belongs to G dash, then tau A inverse belongs to G dash, because this G dash contains all the permutations that are defined on the set G for the particular elements of G. So then tau A inverse, this is by this closed property, this is equal to tau A inverse, and this is equal to tau E. So this is the identity in the set G dash. Now lastly, every element will have an inverse, and this can be easily seen actually from here. This is the identity element, and for every element A belonging to G and tau A belongs to G dash, then A inverse belongs to G and tau A inverse belongs to G dash. So therefore for each tau A belongs to G, tau A inverse is the inverse of tau A. So therefore G dash is a group. So therefore G dash is a subgroup of SG. Now we will show that G is isomorphic to G dash. Now define a mapping. Psi from G into SG by psi of A is equal to tau E. Now, since this tau A is an element of Sg, and in particular, actually, this tau A is an element of G dash, so we will prove that this mapping is an injective homomorphism. So it will mean that this mapping will preserve the operations of G and the operations of G dash. So hence we can conclude that this G is isomorphic to a subgroup G dash of Sg. And in fact, we can also prove that this mapping is a bijection from G into G dash. Then psi A is injective. Then psi A is injective. And this can be seen like this. For this, let psi A is equal to psi B. Then this means that tau A is equal to tau B. And this implies tau A of x is equal to tau B of x. And by definition of the mapping tau, this implies that Ax is equal to Bx. And this implies A is equal to B by cancellation line G. So this is therefore psi is an injection. And we can also prove that psi is a surjection from G into G dash. Now let's choose some element tau G belonging to G dash. Then G belongs to G is such that psi of G is equal to tau of G. So this means that for every element tau G in G dash, there is G in G such that psi of G is equal to tau of G. So thus psi is a bijection from G into G dash. Now to prove that these two groups are actually isomorphic, we only need to prove that this psi is a homomorphism, and that would actually mean that the mapping psi preserves the operations of G and G dash. Now psi of, suppose G1 G2 is equal to tau G1 G2, and by definition of this tau, this is actually equal to tau G1 tau G2. So this is equal to psi of G1 psi of G2. So therefore psi is homomorphism. Now since we have already seen that psi is a bijection, therefore psi is an isomorphism. So this implies, now as psi is a bijection, from G into G dash, and being a homomorphism, thus psi is an isomorphism. So this completes the proof that every group G of finite order n is isomorphic to a subgroup of Sg. Thus, G is isomorphic. To a subgroup of SG. And while going in this completes the proof, and while going in the proof, we have seen that what is the structure of that subgroup of SG to which G is isomorphic. So keeping that thing in mind, we can have an example here. So let's take an example here. Let's choose a group G. Let G is equal to the group Z4, and the Z4 contains the four elements 0, 1, 2, 3. Now instead of writing for the sake of simplicity, we will write 1, 2, 3, 4 instead of 0, 1, 2, 3. So here actually this 0 and 4 are the same elements. So here this 4 is the identity element. Now we have to construct. So by the Cayley's theorem, this Z4 is isomorphic to a subgroup of S4. Now we need to find that subgroup in S4, which was denoted by G dash in the proof of the Cayley's theorem, such that Z4 is isomorphic to that G dash. Now, since Z4 has four elements, so actually we need to compute four permutations from S4 to construct that group G dash. Now let G dash, as from the proof of Cayley's theorem, be the group with permutations, suppose P1, P2, P3, and or let's use the notation that we had written in the Cayley's theorem. Let's write as this is tau 1, tau 2, tau 3, and tau 4. So these are the four permutations in G dash, where from the definition from the proof of the Cayley's theorem, we know what are these tau, how we have to define these tau a's on G, where tau a is a mapping from G into G by tau a of x is equal to x. Now here we can see that our chosen group is Z4, and since Z4 is a group under addition, so in Z4 we can write tau a of x is equal to a plus x, because this tau Z4 is a group under addition. Now let's compute this tau 1, tau 2, tau 3, and tau 4. Then tau 1, this is equal to actually tau 1 of x, this is equal to 1 plus x. And in the formula permutation, we can write it like this. Now the four elements of Z4 are 1, 2, 3, 4. Therefore, tau 1 of x is equal to 1 plus x, means that tau 1 of 1 is equal to 1 plus 1, that is 2. Tau 1 of 2 is 1 plus 2, that is 3. Tau 1 of 3 is 1 plus 3, that is equal to 4. And tau 1 of 4 is 1 plus 4, that is equal to 5. But when 5 is divided by 4, we get the remainder as 1. So therefore, this is tau 1 of x. Now similarly, we can define tau 2 of x. This is equal to 2 plus x. So, or this tau 2, this is equal to 1, 2, 3, 4. Now under this permutation, every element is added 2, so it is 1 plus 2 is 3, 2 plus 3, 2 plus 2 is 4. Now 3 plus 2 is 5, but when divided by 4, that it leaves the remainder 1. Now 4 plus 2 is 6, when divided by 4, it leaves the remainder 2. So this is our mapping tau 2 here, permutation tau 2. Now we can compute the permutation tau 3 of x, and by definition this is equal to 3 plus x, or we can write tau 3 is equal to, this is 1 2 3 4. Now under 1, 1 goes to 4 because it is 1 plus 3, that is 4. Now 2 plus 3 is 5, that is 1. 3 plus 3 is 6, that is 2. And 4 plus 3 is 7, that is 3. Now similarly we can define tau 4 of x. This is equal to 4 plus x, or tau 4. This is equal to 1, 2, 3, 4. Now 1 plus 4 is 5, that is again 1. 2 plus 4 is 6, that is 2. Here we have 3, and here we have 4. So these are the 4 permutations, or we can write these permutations like this. Now 1 goes to 2 here, 2 goes to 3, and 3 goes to 4. So this is this kind of permutation, 1, 2, 3, 4. Now here 1 goes to 3, and 3 goes to 1. Now here 2 goes to 4, and 4 goes to 2. So it is 1, 3 into 2, 4. Now this is 1 goes to 4, 4 goes to 3, and 3 goes to 2. Now this is equal to, this is an identity permutation. So therefore Z4 is isomorphic to the permutation group that contains the element identity element 1, the element 1, 2, 3, 4, the element 1, 3, 2, 4, 1, 3, 2, 4, and the element 1, 4, 3, 2. So this was obtained from the proof of the Cayley's theorem, that this is the subgroup of S of G. So this is actually the subgroup of S of 4, and Z4 is isomorphic to this subgroup. Now similarly we can take one more example. Similarly Z2 cross Z2, which is actually the Cayley's 4 group, and it contains the elements of the form identity element X, Y, and XY. And it can similarly be seen that this group is isomorphic to a subgroup of Z4, and it contains the elements, the identity element, the element 1, 2, 3, 4, the element 1, 3, 2, 4, and the element 1, 4, 2, 3. So with this we stop the lecture here.